Let's illustrate problem 1. I've toggled a switch on the back of the machine, and if the apprentice would draw problem card number 1, it would read as such. The motor runs noisy. Starting torque is reduced with conduction lost on one motor winding. And you're advised to write your answer to the above problem in the space below. Okay, for problem number 1, we're going to push the start switch. Both motors go in, and it appears though that the motor has lost a phase, the same phase on both motors. That would lead your apprentice to believe he has a single phase condition. Now in reality, a 3-phase AC motor wouldn't start on a single phase condition. That's not really an accurate illustration of a problem that a man might encounter in the mine with 3-phase AC electric motors. But this trainer, to illustrate the 3-phase motors, you only have 120. You have a phase and a neutral. And to show 3-phase motors, you'll note there's a jumper from phase 1 to phase 3. In a real life scenario, if you had a connection between phase 1 and phase 3, that would be a short circuit. That would be a catastrophic electrical event. It would, with assets would be damaged. It would blow things up. But this is a trainer. We have a drawing that shows a jumper from phase 1 to phase 3. Phase 2, if you would note, is common to all 3 lights on the A motor. It's also common to all 3 lights on the B motor. Common sense would tell you that phase 2 is the neutral of the 120 volt input. And phase 1 goes to light 1 and light 2. If you follow phase 1 out, L11 to B motor from light 1 to light 2. That's 2 of your lights are lit by only one phase. The neutral, phase 2 is the neutral. Now let's do phase 3. Phase 3, a jumper from phase 1. In real life, that's the same power. Over to light number 3 and light number 3. The third light on both the A motor and the B motor is supplied by a jumper from L1 to L3. An apprentice or an electrician troubleshooting a 3-phase motor underground would never find a situation like this. This is not realistic. But we have a drawing, and the drawing shows this is how the panel is wired. This is how it works. So using the drawing, let's go through the panel. Okay, before we begin to troubleshoot, let's don our low and medium voltage gloves. And we're going to de-energize the panel. And lock and tag. Removing the key from the lock, place it in our pocket. All right. And we're going to test this for electricity before we handle anything. I've turned on a voltage detector. I'll test it on a known live circuit to show it's correctly operating. And as you can see, it is working. And then we're going to use it to check for any standing electricity. No portion of the circuit appears to be energized. You always test it before you touch it. This instrument here has a built-in flasher that assures you that the instrument is operating. It is on by flashing a little pulse there. That doesn't indicate power. This is how it acts if there's power. It locks on, steady tone. and it'll turn itself off after a moment. Now, we decided that we've lost a phase. So after I've determined the power is indeed off, let's remove the gloves. I'm going to make continuity tests. We'll zero our instrument. The instrument is zeroed. And here we go. Our first test on the drawing is shown from F1 fuse, the line side, to the line side of F3 fuse. Now, we don't have a circuit. As is indicated by the meter, there is no circuit. Okay. There should be, according to the drawing, there should be continuity there with virtually no resistance. And in this case, it shows none. The problem would be the L3 power lead is broken on the line side of the F3 fuse. And that would be how the apprentice wrote his problem's answer down. Problem number 2. If the apprentice should draw this problem for his state electrical examination, it would read as follows. None of the control circuit will operate. The motors will not run. That's it. None of the circuit will operate. Motors won't run. Let's toggle that problem and show what the trainee would see. He's prepared to run. He has power. Presses the start switch. Nothing happens. Okay. This is basically, he has no clue. There's no clue given. Has no control power. So what we're going to do is lock and tag. We're going to take the power away. We're going to use our voltage detector, turn it on, and test it on a known live circuit. That's to check the operation of the voltage detector. And we're going to check for any AC power present. Doesn't appear to be any. That's good. So, we can remove our gloves after you've determined that there's no AC power. I'm going to calibrate my instrument by shunting the leads together and zeroing the instrument. And we, with no clue other than it won't run at all, we have no choice but start the beginning of the circuit. And the beginning of the circuit illustrated here is from the line side of the L1 fuse, or F1 fuse. It proceeds through the fuse. We have a circuit. And then to the line side of the breaker, we have a circuit. Through the line side of the breaker, we have a circuit. Now, to keep ourselves in a semblance of order there, to keep ourselves from becoming lost, let's take all 3 of the line side wires to the breaker through at one time, and then go from there. This is the F2, L2 lead to the F2 fuse, through the fuse, through the breaker, and we're good. Well, we have another F3. L3 goes to the line side of F3. Reading it, we're intact. To the top of the circuit breaker, line side of the circuit breaker, and through the circuit breaker. Okay, The next place that we would go if no control operates. Well, our control circuit originates on the bottom of, or the load side of 1CB on leads L11 to F4 and lead L12 to F5. I'm going to start with L11 and read to the line side of the F4 fuse. L11 is here to the line side of the fuse. Uh-oh, the read's open. Let me check my instrument. No, my instrument is functioning correctly. F4 fuse, line side, that reads open. Let's try, just for curiosity's sake, L12 to the line side of F5. And we have a circuit. Okay. The portion that we just checked to the print is from here, the load side of 1CB to the line side of the F4 fuse. And it is open. I'm going to toggle the switch in the other direction just to check ourselves. And I'm going to take the problem away. This is how the circuit should read. Line side of F4, and we have a circuit. With the switch toggled, we do not. To properly complete the form, the apprentice should write on the lines indicated, control lead broken between circuit breaker terminal L11 and control fuse F4. That's that. Problem card number 3. Should the apprentice electrician taking the test draw problem card number 3, it would read as follows. None of the control circuit will operate. Motors will not run. That's exactly the same problem we had for problem 2. And we're going to give it a try here, see what happens. We're going to push the start switch. Yep, nothing happens. So, you don't really have a basis to start troubleshooting other than at the beginning. It says none of the control circuit will operate. So it could be anywhere, or most anywhere in the circuit. What we'll do is let's take the power off, lock and tag. We're going to stow the key. Now we're going to check for voltage to make sure that indeed the power is off. I'm going to check on a known live circuit. And I have power there. My voltage tester is operational. Now let's see if we have any power on the board. There's no power indicated. I believe we're good to go. We can take the gloves off and begin our troubleshooting. To begin, we'll calibrate our instrument. And it's very well zeroed. No calibration necessary. Let's start at the source. There's no control circuit. We don't know what portion of the control circuit is absent. So we have no choice but to start at the beginning of the circuit. I'm going to check the F1 fuse. And it is good. Then from the F1 fuse it goes to the line side, 1CB. As you can see, the meter indicates a low resistance connection. It's good. Now I'm going to go through to the load side, 1CB. Again, we read well. I'm going to stop at that point and bring the other two phases up to the same level. F2 fuse. It's good. To the line side of 1CB, through 1CB to the load side. That's good. Now for number 3, phase 3. The fuse reads good. No resistance there. Line side of 1CB is good. And the load side, 1CB. So we've determined that we have no problem from the beginning to here. Now let's proceed on the load side of 1CB. L11 would be a good place to start. You develop patterns in your troubleshooting, guys, and you know, I tend to go from left to right and from top to bottom. L11 to F4 is intact. And through F4, F4 reads good. And from F4 to H1, we've checked this portion of the circuit from L11 through the fuse to the primary of the control transformer and found no open wire or fuse. Let's begin with the next one. L12 supplies the other side of the transformer. And we're here. Let's go to F5. Uh-oh. I don't have a circuit. The wire from L12, the load side of 1CB, to the line side of F5 appears to be open. Let's try our toggle here. F5, and it's open. To complete his exercise, the apprentice would have to list the problem on his answer sheet, and his answer would read, control lead is broken between the circuit breaker, load side of CB1, and the line side of the F5 control fuse. It's lead 12. That's it. Problem number 4. Should the apprentice draw this problem at the state electrical certification examination, it will read as follows. None of the control circuit will operate. The motors will not run. Well, we've had this problem before, at least a couple of times, and both the other times were different problems. I assume this one will be too. Let's check it out. And press the start switch. Nothing happens. Okay. First thing we need to do before we begin to troubleshoot is remove the power. There's not really a starting point here, and you know, one part of the circuit not operating, so we have to begin at the beginning. We're going to lock and tag. Stow the key. I'm going to use this voltage detector and I'm going to test it first on a known live circuit. And we're good, it's working. Now let's see if we find any power on the board. And there doesn't appear to be any power. The little pulsing flash that you see on the tester, that's an indicator that the tester is working. When it senses power, as you probably note, you hear an audible tone and see a constant light. We're not finding that on the board. I'm going to turn that off. We can take the gloves off now that we're safe. We have no power. Take our test instrument here and before we use it, let's calibrate it. This thing's running really well today. We're not having to do any adjustment. It's in good shape. With no symptom exhibited except it won't run at all, we have no choice but to begin at the beginning. The input to the panel. See, lead 1 comes to the F1 fuse. The line side of the F1 fuse. Let's read the fuse. We'll read through it, and it reads good. Now we'll go to the line side of 1CB. Again, we have continuity with no resistance. Now to the load side of 1CB. We're reading through the circuit breaker. If the circuit breaker were open, you wouldn't read anything. It would read open. And with it closed, we're supposed to read continuity with low resistance or no resistance, and we do. Now, that handle, it's in the on position, it's in the closed position. You'd think for sure the circuit breaker is closed and doing as it should, but as a matter of fact, on mining machinery, a circuit breaker failure is not at all uncommon. Before you can say with any certainty that the breaker is either open or closed, you would have to use an instrument to read it because the contacts are not visible. That is why a circuit breaker is not considered to be an adequate visible disconnect, because the contacts are not visible. You can't visibly determine that these contacts are either made or not made or open. But we've determined that this one is good with this instrument. Now let's move on to F2. L2 goes to the line side of the F2 fuse. We're reading through the F2 fuse. That's good. No resistance there. To the line side of 1CB. Through 1CB to the load side. It's intact. And I'm going to break that off there and stop and bring the other one up to speed. Come up with the other lead. Here we go. L3 through the F3 fuse is good. The line side of the breaker. Load side of the breaker. Now we've systematically checked all of this portion of the circuit. Now, the control circuit's not operating. Let's read the control portion of the drawing, of the print here. It begins with L11 and L12 supplying the primary control fuses, and through the primary control fuses to the primary of the control transformer. Let's check that part now. We'll start off with the L11. It's on the load side of 1CB, and it goes to F4. And we read good. No problem there. We're going to read through F4 from the line side to the load side. The fuse is intact. And then to H1. And it appears to have a little bit of resistance there, but it's still a competent circuit. What we've just checked from L11 through the fuse to the primary of the control transformer. Let's do the other side, the L12. Load side of 1CB to F5. F5 is here, and it's good. No resistance. Through the fuse, it's still good. To the H2, it reads well. It still reads a slight resistance. You know, there are a few perfect circuits, and this is reading less than 1 ohm. There's a small resistance there. That should be, or that could be the contacts of these probes here. I'm not making a good solid contact, but it's a good circuit to the primary of the control transformer. Let's read the primary. The primary should read a circuit, and it does. 1 ohm. So all is well. To further check this control circuit, we've determined this portion of it now is all right. Everything is good. It's as it should be. To continue our troubleshooting here, we're going to begin with the secondary side of the control transformer, the X1 and X2 terminals. And the X1 terminal is here. And I'm going to read to the load side of the F6 fuse. And I have a circuit from the line side of the F6 fuse. Now I'm checking the load side. And we're good. Now, let's keep ourselves in order here. I'm going to complete my control transformer and fuse checks by reading from X2 on the transformer, that's the one on the right, to the line side of F7. Uh-oh. I don't have a circuit. The line side of F7 reads open. The problem indicated is from X2 terminal, secondary of control transformer, to the line side of F7 fuse. The wire connecting the two are open. Should an apprentice draw a problem like this, a control problem like this, where nothing operates, he could find more than one scenario. It's possible that he would find an open fuse. These, at the various testing centers there, they use different ways to do the same problem. As you can see, we've had the first 4 problems. 3 of those have been motors will not run. And they've all been different problems. Ours have been open wires. It could very easily have been an open fuse. So, but by checking in this fashion from the line side of the fuse to the load side of the fuse, if the fuse is open, it will be determined. Our problem here, should the apprentice draw this, his answer will be, he has a control lead broken between transformer secondary terminal X2 and the line side of the F7 control fuse. That's it. Problem card number 5. None of the control circuit will operate. The motors will not run. If you've been following these closely, you'll note that we've had several of these before, exactly the same wording, but all the problems have indeed been different. And looking at the print, you know, those of you who are more discerning will note that there are a number of things could cause this symptom. The only way to determine what it is with the instrument. That's what we're going to do. Let's try it. See if the problem is as reported. If you're troubleshooting in real life on the section, it's good to try it, because often the problem is not as reported. But in this case, they're right. It won't run. Let's put our gloves on, low and medium voltage gloves. Take the power away. We're going to lock and tag this. I'm going to use this fluke voltage detector to see that indeed the power is off. Before I trust this, I'm going to check it on a known live circuit. And the voltage tester is operational. Now let's check the panel. Note the intermittent flash on this particular unit. This model voltage tester has a built-in feature that flashes a steady cadence to indicate the voltage tester's working properly. That's not indicating power. The flash is just to tell you that it is working, it is on. This is indicating power. You'll note the light stays on constant and you have a tone. We've determined that we don't have any power on this. We can take the gloves off. As the problems that went before, nothing will operate. None of the control circuit will operate. To avoid possibly missing the problem, you want to pass it to beginner troubleshooting. Let's start at the beginning. In the beginning, L1 was to the line side of the F1 fuse. Oops, I forgot to calibrate this instrument. Let's look at that. It's reading on 0. I was okay. Here we go. F1 fuse reads good, and we're going to go to the line side of 1CB. It also reads good. Let's go to F2 fuse. It reads good. No resistance there. The line side of the fuse. Load side of the breaker. All's well. F3 fuse. Line side to the load side. Reads good. Line side of the fuse to the line side of 1CB. Reads good. Load side 1CB. Reads good. So what we've just checked, we've read the fuses and 1CB. Everything is intact in this part of the circuit. The control is the portion of the print that's not operating. This circuit, the control circuit, originates at the load side of 1CB. So I'm going to start our testing there. Let's begin at L11, the load side of 1CB. There's a wire that goes to the line side of F4. If you can see, there's no resistance. That's good. Let's read through F4. And again, it's good. And then to the primary of H1. And, I lost my connection there. That reads good. I thought we had it there for a moment, and it's not it. Here we go. We've just read this part of the circuit to the transformer. Let's check the other leg, L12 to the line side of F5. F5, line side, no resistance there. Through it, the fuse is good. Let's proceed to H2. Again, it's got a little resistance, like less than an ohm. That would not indicate a problem. That's probably a poor connection of the probes. To complete the primary circuit, let's read the primary of the transformer. From H1 to H2. We should have a circuit of comparatively low resistance. And we do. It's intact. We've determined that this portion of the print, we've checked every wire. And we've checked every component, the fuses, the breaker, and the primary of the control transformer. All is well. Let's proceed. We're going to check from the X1 portion, the terminal X1 on the control transformer, to the line side of the F6 fuse. Here we go. X1 terminal, line side of F6. Well, let me check my meter. That should read. And it doesn't read, but the meter does. Let me try it again. I can't make it read. That would indicate a problem. We have an open wire. from the X1 terminal of the control transformer to the line side of F6 fuse. From here to here, I have an open wire. I tell you what, let's operate the toggle just to make sure that I'm right. X1 terminal to F6 fuse. Here we go. I'm on the F6. This is X1. And with the toggle operated, it does read. It reads as it should. That would conclude your test and be sure that you're done, sure that you found the problem. To complete the examination, the apprentice would need to write a written answer for his problem as the control lead broken between the transformer secondary terminal, which is X1, and the line side of the F6 control fuse. That's it. Problem number 6. Should the apprentice electrician draw problem card number 6, it will read as follows. The control circuit will sequence through properly and the motors will run. However, everything falls out when the start switch is released and the motors stop. Well, I'm glad we have something moving anyway. All the problems prior to this, nothing worked. Let's give this a go. We'll press the start switch. Motor A started first, then after the timed interval, motor B starts. I'm ready to go about my business. I turn loose the start switch though, it quit. That is a problem. We spoke earlier of the holding circuit. Some folks illustrate that as a sealing circuit, holding circuit. They mean the same. But if you see on the drawing, you have a normally open momentary start switch. When you depress the switch, you energize the remainder of the circuit. And when the circuit is energized, when A contactor pulls in, A coil is energized, it has a circuit, A contactor closes, A auxiliary also closes. The A auxiliary is located on the side of the A contactor. I'll point to it closer when we have the power off. And B contactor also has an auxiliary. It's located on the side of B contactor. When they close, it provides a path around the start switch. So you can release it. After you release the start switch with A and B interlocks or auxiliary contacts closed, you have a circuit around it. That's a holding circuit. Now people would think that you could use just a snap switch, a switch that would remain closed. When you want to start it, you close the switch and it remains started. But there's a problem with that. On a motor control circuit, you have a thermal overload. If you should stop the motors with the overload, have an overload, draw too much current, and before you damage the motor, the overload opens. If the start switch was in a snapped closed position, as soon as the overload cooled and reset, the motor would start again. And without an operator depressing a switch, you wouldn't know when it were going to start. It would just start when it become ready to start. That's undesirable on a piece of equipment. You need to have a definite control where someone presses a button, operates the circuit, started. That's the point in using the momentary. And with the interlocks, give you a holding circuit to allow you to turn it loose. Now, when it stops, these normally open contacts here, they revert to their normally open status. And when you release the start switch, it reverts its normally open status. So nothing's happening until you press the switch. You initiate by closing the switch to start the motors. We've determined, where our problem could lie. Let's take the power off. We're going to lock and tag. Stow the key. I'm going to use this voltage detector here. I'm going to turn it on. I'm going to check it on a known live circuit. This extension cord, this is what we power the panel with. It's a known live circuit. And the voltage detector indicates with the light and with the tone that you have power. So it's tested. I know it's operational. Let's test the remainder of the panel with it. You'll note the little pulses of light. That's an indicator that the voltage tester is operating. When it finds power, it locks on, gives you the tone and a constant light. I'm not finding any power. I believe we're safe here. I'll turn this off. Take the gloves off. After we've taken the gloves off, let's take our test instrument. I'm going to check it for calibration. We're accurate there. Now I know that the part of the circuit associated with the holding circuit, what we don't have is this part here. Let's begin our checks there at the beginning of the holding circuit. That's the part we don't have. So I'm going to begin our checks there. And you can see the holding circuit originates at the load side of the stop switch or line side of the start switch. The point on the print's marked 3. There's no corresponding mark on the panel, but we know where that's at. Let's check here. From 3, it goes to the A auxiliary. And wow, neither of the terminals on the A auxiliary show a circuit. Now, according to the drawing, I should have a circuit there from 3 to the A auxiliary. Well, let me check this meter again. Make sure it's good. Yep, it's good. To the A auxiliary. Nothing happening here. That would lead you to believe that the wire that connects in this case, it's the line side of the start switch to the A auxiliary is open. Let's toggle the switch here just to make sure. You remember that before it read open. The wire read open. Let's check it now. Line side of the start switch, A auxiliary. Now with the problem toggled, with the problem removed, it shows continuity, it shows a circuit. With that wire open, the holding circuit is defeated. It's the same as having one of these switches open. You don't have a path for the current to hold the contactor coils in when you release the start switch. Right there. To complete the exercise, the apprentice would write his answer as control lead broken between line side of start switch and A auxiliary contact. That's that. Problem number 7. Should the apprentice draw problem number 7 at the testing center, it will read as follows. Motors try to run all the time. When the stop switch is pressed, the motors stop. However, when the stop switch is released, the motors restart. Well, that's a pretty interesting problem. All the problems prior to this, it won't go. Now here we got one that won't stop. Let's give it a try. We're going to put the power on the box. Still locked out from the last one. Okay. It's not illustrated on the print, but there is an on-off switch to take power on and off the box, and it's there. I'm going to turn it on. Wow. I didn't hit the start button, but as soon as the power is on the box, it takes off. It started without the advantage of pushing the start button. Let me hit the stop. Well, that's working correctly. The stop button did turn it off, but according to the problem illustration here, when I release the start button or the stop button, it restarts all by itself. Now that is a problem. I'm going to use this switch to turn the panel off, and let's take the power away. We're locked out. Let's stow that key. The agencies don't consider a panel to be, or a machine to be, locked out if you don't take the key with you. I'm going to check and make sure the voltage is indeed off with this voltage detector. We'll check it on a known live circuit. Note the tone and the light stays on constantly. This model of voltage detector, and it has intermittent flash to show you that it is powered up and on. I'm going to check. Don't appear to have any electricity here. The panel appears to be de-energized. Okay. I believe we'll be okay to take the gloves off now. Make some continuity tests. Referring back to our drawing, before this panel begins to operate, you're supposed to close a switch. And it's a normally open switch. It's momentary. If you close it, it should complete the circuit and begin the panel operation. And then when you release it, it should open. When you release it, the circuit should be maintained through the holding circuit, through the A and B interlocks, the auxiliaries that we just checked those just a few minutes ago. The auxiliaries here. They should maintain the circuit. But with it not started, you have an open switch here and you have an open switch here. Nothing should happen. But on our problem, as soon as it's energized, without the start switch being depressed, it takes off, it goes. I believe our problem's in the start portion. We'll begin by checking the start switch. I'm going to place one of my meter probes. Let's zero this instrument. I'm going to place one of my probes on the start switch, line side being toward the source, the load side's toward the work, and read to the other probe. According to the drawing, it should be open, but in fact this switch reads closed. This switch reads made. The drawing shows this open, but as you can see, watch the meter. It reads made. That's our problem. To complete his exercise, the apprentice would list his problem as the start switch is shorted closed. Now, there is another problem that could possibly cause the same effect, and that would be that the A and B interlocks both be shorted closed. It's highly unlikely. To determine for sure which way the problem was, you would need to isolate the components in question and read them with an instrument with the wires disconnected. And it seems unlikely that both auxiliaries would be bad. Start switch shorted closed. That's that. Problem number 8. Should the apprentice draw problem number 8 at the testing center, it would read as follows. The B contactor picks up 1 second after the start button is pressed. The A contactor doesn't pick up at all. The holding circuit is not maintained when the start button is released. If you remember from the running the panel with no problem at all, the sequence of events: A contactor goes immediately when you press the start button, and after the time delay, B contactor goes. Purpose in the time. Should this circuit be controlling, say, 2 large induction motors? The inrush of current to start the A motor would be at a level where if B motor started at the same time, the short circuit protection in the motor circuit protector, such as this breaker here, 1CB, would operate, would trip. So we need to stagger this start to keep the inrush to an acceptable level to where the main breaker could stay in. Now, that the main breaker is sized for, for a short circuit. 2 motors starting would simulate a short circuit and would cause it to trip. Hence the timing. We're going to stagger this start. The A motor should start first. On the drawing, you can see there's no timer. When you press the start button, A motor goes immediately. The A coil is energized, A contactor is going to close, A should start. Then the timer circuit, TR coil, is energized. After the interval passes, TR mercury tube will close and B coil is energized. It has a circuit and B contactor starts. According to our problem, that's not happening. You press the start button, A doesn't go at all, and B, after it times, it goes. There we go. After many false starts, we finally have a go. Okay, note the A motor is not running. B motor is running. The lights show the B motor. A is not running. Now, according to the drawing, A contactor has to go in and close A auxiliary to have a holding circuit. If you'll look here, the A contactor, it's not in. No holding circuit. When we turn loose the start switch, it should stop. And it does. Let's see what we can find. I'm going to remove the power, lock and tag. Stow this key away. Now let's check and make sure the power is indeed off. And we'll test the voltage tester on a known live circuit. You can see it illustrates power. The voltage tester is working. Let's see if we can find any electricity on this panel. That intermittent flash is a check circuit for the voltage tester. As long as you have that pulsing flash, that means your voltage detector is working. It doesn't mean it's detecting any electricity though. Okay, we're good. We can take the gloves off and make continuity tests. Now our problem states that the A contactor is not closing. And when we operated it, it truly was not. So when you press the start switch, you connect one side of the control transformer, the X1 side, through the start switch to the A coil, through the normally closed A overload micro switch through the normally closed B overload micro switch to complete the circuit to the X2 of the control transformer. Well, that didn't happen. A appeared not to be energized at all, but B did go. Now, for B to operate, the TR coil must be energized, have its path. The TR contacts, the mercury tube for the TR coil must time out and close, and then B get power. It has to have a circuit back to X2, and then go. Now, that part's working. B contactor closed. The part that's not working is between the start switch and A, or possibly from A to AOL. Let's check those parts. Take our test instrument. Let's zero this, make sure we're still calibrated. Let's touch that up just a little bit. Okay. Now, I'm going to read from the load side of the start switch, which is here, to the line side of the A coil, to there. I should have a circuit, but I don't. Let me make sure my meter's working correctly, because that really should read. Meter's working fine. Shows no circuit though. We'll further test this circuit here. Let's check to the remainder of the circuit, like the TR mercury tube. It's working correctly. I should have a circuit to here. I do. TR coil should also have a circuit. Let me check it to here. And I do. So, those readings indicate that from the start switch to TR mercury tube, from the start switch to TR coil, read as they should. But from this point 4 to A is open, doesn't read. I believe that's our problem. To complete the exercise, the apprentice would need to write his written answer as you have a control lead broken between the start switch at terminal 4 and the A coil. And that's that. Problem number 9. Should the apprentice at the testing center draw problem number 9, it'll read as follows. The A contactor picks up immediately when the start switch is pressed. The B contactor doesn't pick up at all. The control circuit is not maintained after the start switch is released. Let's try that and see if that's indeed what it's doing. I'm going to press the start switch and A should go, and you know after the proper interval B should go. The problem says that B's not going at all. Let's see. Now I believe the interval's passed, no B. Okay, it's as reported. B's not going at all. It also said that when you release the start switch, have no holding circuit. That's really not a surprise. The holding circuit's dependent upon both contactors going. Only A's gone. It's as reported, no holding circuit. Let's lock this thing out. Take the power off. We'll stow this key. Now let's check it and make sure the power's off. When dealing with electricity, you can never be too sure because these are often one-time mistakes, all you have. So let's test on a known live circuit. The purpose of this test is to test the instrument, to make sure the instrument's actually working. And it is. Now we're going to check our circuit. That intermittent flash, that's a built-in test of the instrument to tell you that it's on, it's functioning. It's not to indicate power. When we have power, it locks on. You have the tone as well as a constant light. Just see that again. That's how it is with power. We didn't find that though. I'm going to turn the instrument off. We can take the gloves off now. We're certain that we don't have any electricity. We're safe to make a continuity test. I believe the continuity test is in order. It says the A contactor picks up immediately. The B contactor does not pick up at all. Okay. When you depress this start switch, you're connecting the one side of the transformer, X1, through the start switch. When it's depressed, it goes directly to A coil. It also goes to the line side of the TR mercury tube and to the line side of the TR coil. Well, after it goes through A picks up, closes these contacts, allows power to go to these bulbs. They come on. You have a circuit. And then B should come on. TR has timed out after 1 second. These tips close. This mercury tube is now made. B should receive power, follow the same return as A, and B should pull in, close these tips, and have this motor. Well, the A part of that circuit's working. The B is not. There's a timer involved. The timer has to operate before B can work. And the mercury tube, you know. So let's test from the load side of the start switch to the timer mercury tube. That's this part right here. Let's test from here to there. As you see the leg wires for this mercury tube, they're visible. You can see them. They go from the tube itself up to this post. They go from the tube itself over to this post. And there they are. So I'm going to test from the start switch to that point, to the mercury tube, and I have a circuit. So that tells me that the wire is intact from here to here. I know that my wiring is intact. Let's check from the start switch to the timer coil. On the print, that would be from here to the timer coil on the very bottom of the print. On the panel, that's this point here. The timer coil connection is right here. Uh-oh, we don't have it. No reading. Well, let me check my meter. It's reading correctly. I'll start switch to the timer coil. Uh-oh, no reading. That indicates an open wire. The wire that connects this point here to the timer coil from the timer mercury tube to the timer coil is open. To complete the exercise, the apprentice would need to write this answer on his answer sheet. You have a control lead broken between the line side of the timer mercury tube, TR mercury tube, and the line side of the TR coil, open wire. That's that. Problem number 10. If the apprentice draws this problem at the testing center, it'll read as follows. The B contactor does not close even though all the other contactors and timers have operated. The holding circuit is not maintained after the start switch is released. Okay, let's power this machine up and test that. Make sure that's indeed what's going on. It's still locked out from the last problem, but we can get that going in just a jiff. here we go. Reported the B contactor doesn't go. Let's try it. Indeed, it does not. Now, it said the timer operated. I don't know if the sensitivity of these cameras and mics here can pick that up, but I heard that timer operate. Is it possible that my crew heard this? Well, let's try it again and see, can you hear it? Listen close. There it was. Did you hear it? Okay. The timer operated, but the B contactor still did not go. Let's look at our map here. Let's see a print. Okay, we pushed the start switch. A went. We had power to A. Went through the overload switches. They're normally closed on AOL and BOL. Those micro switches were made. It went back to the transformer. We have a circuit. It went to it, through it, and then back away from it. We have a circuit. It's complete. Now, before B can go, the timer, which is the coil for the timer, is energized at the same time A is. They're simultaneously operated, A and the timer. The timer is energized. We heard it operate, and it has a circuit. We heard this connection made, but B didn't go. Note that when I was illustrating the A contactor closing, we showed a circuit. When we made the start switch, it went to the coil, through the coil, and then returned to the transformer. The timer did the same thing. To the coil, to the TR coil, through it, and then returned to the transformer. We hear this contact make, but B doesn't go. Taking power to the device is only half the circuit. It has to go away from the device as well. I suspect that's where a problem lies. So let's take the power off this machine, lock and tag. I'm going to stow this key. Let's test to make sure the power is indeed off. I'm going to test this detector on a known live circuit. You hear it, you can see it. That's what it would sound like if you had power, and that's what it would look like. I'm going to check for power on this panel. I'm not finding any. Note that little flash. That's not indicating there's power here. It's indicating the voltage tester is turned on and it's operating. We don't have any power on. It would be locked on and staying with an audible alarm and an uninterrupted light. I believe we're safe to take the gloves off and make some continuity tests. Now we believe that TR contact is going in. We heard it. It may not really be made though. Let's check things out. The contact could be made and the wire could still be interrupted. So I'm going to read that part of the circuit first. I'm going to read from the load side of the start switch, load side meaning toward the work, to the TR mercury tube, line side of the TR mercury tube. As you can see by the swing of the needle, that shows no resistance. It's in good shape. Next part of the circuit would be same place from the load side of the start switch to the TR coil. Let's see if that's good. We believe we heard it operating, but let's check and make sure the wire's intact. Yes, it is. There was no resistance to the TR coil. It's doing very well. Okay. The next point to test from this, the line side or the load side of the TR mercury tube to the line side of B coil. And now note on the print, that's a very, very small line. That's for the expediency of the drawing. It's not necessarily how things lie or the order they lie in on a machine or how close they are in proximity to each other. That illustrates how it's connected. And as a matter of fact, this TR mercury tube was quite far from the B coil. It's all the way down here. Let's read that. Yeah, it reads good. Look at that. I have a full scale needle deflection. It shows 0 ohms resistance. That wire's great. It's a good connection. Well, so far we've checked from power to the mercury tube to the coil. We've checked from the mercury tube to the B coil. Let's check from the B coil to its return. You know, power to the circuit's only half of it. You have to have power away as well. So I'm going to check from the B coil. The first point on its return path would be AOL. This is the return side of the coil. This is after the work is performed, the electricity has to have a path back to the source, the return side. That's on the right of this particular contactor to AOL. There's a micro switch. Its terminals are underneath. I don't know if you can see those. AOL. It's not reading. It's showing an open circuit. Well, just to check our as much of the circuit as we can, try to isolate it, I'm going to read from the return side of A contactor coil to AOL. That will take at least part of this away. Well, let me do that. We're going to try and narrow this problem down, as small area as possible. This is return side of A coil. Again, it's on the right on this particular panel. Look at here. Hey, it's reading. We have no resistance, so that tells us that this part of the wiring is okay. We pretty well knew that because A contactor worked, but let's be thorough in our test. The other part of the circuit I can check to further isolate it from the return of TR coil to AOL. Let's try that. This is the return side of the TR coil, the timer coil. It also returns through AOL. Looky here. It's got a full circuit, full scale, no resistance to it at all. So that circuit's intact. Now if you recall, read from here to AOL and it reads good. We read from here to AOL and it reads good. But from B, it does not. B's not operating. We believe, and our meter indicates, that this portion of the circuit from the return of B to this connection here is open. The return side of B coil to AOL has an open wire. To complete the exercise, the written portion of his answer, the apprentice should write, you have a control lead open between the B coil and the A overload contacts. And that's that. Problem number 11. If the apprentice should draw this problem at the testing center, it would read as follows. Control voltage is available, although none of the control circuit will operate. Neither motor will run. This problem in wording is really similar to some of the other problems that we have. You know, none of the motors will run. You press the start switch, nothing happens. That's basically the same symptom we have here. It has a qualifying statement though, control voltage is available. Now, that tells you a whole lot. If you know that you have control voltage available, then that tells you This part of the circuit's intact. This part of the circuit is intact. It's stated control voltage is available. So you know that everything is cool all the way to there. That's going to eliminate a great big part of your testing. You know control voltage is available. So let's try the panel. Just make sure that's indeed as reported. It says that nothing will run. We don't have to take that at face value. Let's read it, or let's try it ourselves and see. That was an accurate report. Nothing will run. So, you know, I can offer you this advice. In a less controlled environment where you don't know exactly what the problem is and the problem could be varied, it won't always be as reported. That's what someone thinks is happening. You need to make your own test and really check things closely to be sure the problem is as reported. This can keep you from making a lot of unnecessary checks and possibly even being fooled by it. But this one is as reported. Nothing will work. It says control voltage is available. Nothing happening. Let's lock it out. I'm going to take the power away. Let's put some gloves on here. Take the power away. I'm going to make sure the power is removed. To test my voltage detector, I'm going to check it on a known live circuit. It indicates power. We have a constant light as well as a tone. Very annoying tone. Let's try this. Note the intermittent flash, little pulse. That's to give you an indication that the voltage detector is turned on and it's working. It's not detecting voltage. We saw what that was like. A real loud tone and a constant light. Not flashing, but on, period. This doesn't show any power. I believe we're safe to take our gloves off and make some continuity tests here. We're going to calibrate our instrument. This instrument stayed true for us most of the day. It's just staying on zero when the leads are shunted. You have to test that though. If you're going to take a reading, you need to have your instrument be as accurate as possible. Now we know that control power is available, but we don't have anything operating. I'm going to start at the line side of the control fuse, F6. The problem doesn't say where control power is available to. I'm going to say it's right here. I'm going to put 1 meter lead at F6, read to X1. As you can see, just a small amount of resistance there, 1 ohm. Possibly that could be, you know, the meter lead's not exactly solid, but that's not enough to shut this machine down. I'm going to read through F6 to check the fuse, and it's good. From F6 to the stop switch. Stop switch is a normally closed switch. No resistance there. That's shows a perfect circuit. Let's read through the stop switch. No resistance there. From there, the next point from the stop switch would be the A auxiliary. Again, perfect circuit. And to the start switch. No problem there. Well then, I'm going to read the start switch. It's supposed to be normally open. And it shows normally open. I'm going to press it with my thumb to make the circuit. Looky here. No problem. No resistance. I'm reading through the start switch. So I know it's not a bad switch keeping it from running. I'm going to go to the load side of the start switch and read to a coil. No resistance there. A coil is intact, or the wire between the start switch and A coil is intact. I believe we should follow this on out. Let's read across this coil. Now you know that these problems are all induced by a toggle switch, and it's not going to be an open coil, but proper procedure would make you check that coil. If you were doing this in a real life situation, you would check that coil to make sure that the coil wasn't open, and it's not. This coil's reading, looks like approximately 28 ohms. Well, let's read this one here and see if it reads a comparable amount. Again, it reads 28 ohms. Well, we have two of them reading the same. Let's take the other side of A coil. From A coil, it goes to A overload. Again, no resistance. From A coil to A overload, reads a perfect circuit. On the drawing, that's here to there. We need to find this one quick. We're running out of parts to check, aren't we? Looky here. I'm going to read through the overload relay. It reads good. No problem there. I'm going to go to B overload. And that's still good. Finally to the other side of B overload. Again, look at that meter. There's no resistance. Well, from B overload, the next point on the print, BOL goes to the load side of an F7 fuse. Uh-oh. Now that's no good. Our drawing shows an uninterrupted wire from BOL to the load side of F7 fuse. But our instrument says the wire is open. And it is. It doesn't read. This is the return side of the circuit. After the work is performed, in this case the work is we're going to convert electricity into magnetism. Use that magnetism, it will be further converted to mechanical energy and pull a contact in. Okay? That's the work. We're going to close contactors. But in order for this circuit to be complete, it not only has to have a path to the device, but it has to have a return from the device. That's where we're lacking. This wire is open. Our meter indicates a broken wire. To complete the exercise, the apprentice would have to, for his written answer, list control lead broken between return side of BOL and load side of F7 fuse. That's that. Hello, I'm Dave Terry and I'm at the Elk Run Training Center, and today we're going to do an exercise with the basic AC electrical training panel to prepare apprentice electricians to take the state electrical examination. We're going to illustrate several problems. Hopefully it will be every one that may be encountered on the test, I believe so. And not only to do the problems for the test for certification, but we hope to prepare our apprentices for proper, safe troubleshooting procedures as well. Before we put any problems on the panel, let's show the correct operation of the panel, how things should work. We have two line starters. This type of panel is commonly found on a belt starter. It'll have two motors to run, an A motor and a B motor. The motors are illustrated on this panel by these lights. These 3 lights in this grouping on the left are for the A motor. The 3 lights in the grouping on the right are for the B motor. Each light symbolizes a phase, an energized phase. When the motor is started, it has 3 phases energized. Now, we have 2 contactors, an A contactor and a B contactor, 2 thermal overloads, an AOL, a BOL. We have a main breaker, a transformer. You have a stop switch and a start switch, a timing relay. With the fuses, that pretty well covers the entire group of components. These are illustrated on the print. It's the breaker, fuses, the A motor, these 3 lights tied together, the B motor, the AOL, BOL, A contactor, B contactor. And you have various control components, beginning with the primary fuses for the control transformer, the control transformer. Notice it's a 1-to-1 isolation transformer. It's 120 volt input, 120 volts output. You have F6 and F7 fuses, the secondary control fuses. You have a stop switch. It's a normally closed, momentary stop switch. You have a start switch. It's a normally open, momentarily closing. An A coil, which is the actuator for the A contactor. A B coil, which is actuator for the B contactor. TR mercury tube. The TR mercury tube is this component here. By the fact that it's shown with wings, those diagonal lines off one of the points there, not on the bowl but on the other, that symbolizes it is a timed mercury tube. And the timer portion of this is the little beige colored box on the side. The TR has a coil that operates it. The TR coil is shown right here on the bottom of the print. The TR coil on the panel is this part right here. To operate, the timer coil makes a magnet, pulls some mercury through an orifice into the bowl, makes a contact, and then completes the circuit. We have AOL and BOL, the contacts. Note that the overloads, the thermal overload, there's basically 2 separate circuits for a thermal overload. You have the motor currents that pass through the thermal element of the overloads. You'll note that they're drawn in bold lines. They're in series with the motor and the contactor. Motor currents pass through the thermal element of the overload. When the overload reaches its set point, what it's rated for, it's a bimetallic strip. It will flex, and when its flexion operates the micro switch. Now the micro switch for AOL, is on the return side of the control circuit. It doesn't break the motor circuit at all. It breaks the control circuit. When the control circuit is broken, A coil no longer has a complete circuit. It's no longer an electromagnet, and it allows A contactor to come out. The A contactor has return springs that force the contacts apart if you don't have an electromagnet. That's here. The BOL, same scenario. The BOL has 2 elements. It has the actual current carrying element for the motor. The heater strips or the heater elements are in series with the motor and the contactor, and they're subject to motor currents. If the motor draws enough current to reach the set point or the rating of the thermal overload heater strip, it's a bimetallic strip, and the 2 metals involved, they respond differently to current. They'll bend, and when they bend, when they flex, they operate the BOL micro switch. Note that the BOL micro switch is not in series with the motor circuit. It's in with the motor control circuit. So when it opens, in the event of an overload, it takes away the return path for the coils on the contactors. When the coils lose power, they drop out. They're no longer an electromagnet. The contactors are equipped with return springs that push the contact tips apart, take the current away from the motor, and stop it. Note that AOL and BOL are in series. By in series, that means there's one path for current to flow. Current has to flow through both overload contacts in order for either coil circuit to have a return. So if either motor is overloaded, both motors stop. Okay, that's a basic run through of how the panel works. Now let's start the panel and show you what the proper operation looks like. We're going to press the start switch. Note that A motor starts first. After a short time delay, B motor starts. After it's running, after both motors are running, you can turn loose the start switch. It has a holding circuit. The holding circuit is provided by this portion of the controls. You'll note that you have two auxiliaries. Some folks would call that an interlock. You have two interlocks that are normally open. When they're powered, when the coil is powered and the contactors are pulled in, the auxiliaries close. And by closing, they provide a path around, a parallel path around the start switch. The start switch reverts to its normally open state, and the current is then directed through the auxiliaries to provide a holding circuit. That allows you to not hold the start button. You wouldn't want to latch a start switch on a motor control, because if so, when you had an overload, say the overload operated, if the start switch was latched, it would, open and stop for the overload. When the overload cooled and the switch closed again, start switch was latched, it would just restart without a control, without someone having to start it. It would restart by itself. That's undesirable in machinery controls. So we have a normally open start switch. We're dependent upon a holding circuit through interlocks, and if we have an overload, anything stops, it reverts to its stop state, its normally open state, and it has to be restarted manually. Okay, normal operation. You press the start switch, that's here. You have current flows immediately without interruption to A coil through the overloads and returns to the control transformer. You have a circuit. It's made a path all the way around. A pulls in. When A closes, when A coil is energized, these contacts close. The motor is energized. The motor being illustrated by these three lights, as shown on the drawing, these three lights. Now, when A starts, you're still having to hold the start switch. You don't have a holding circuit until B starts. Now, the timer, its coil is being driven now. The mercury is being pulled through the relay. When the mercury makes the contacts, B coil is energized and it pulls in. It has a circuit. It's the same return as A through the overloads. B closes right here. These contacts close. The B coil is a magnet. It pulls those in, and it has a return. The B auxiliary closes. At that time, you can release the start switch, and it will remain running until such time as you stop it with the stop switch, or if you would have an overload open, that would stop it, or if you would lose power, everything reverts to its normally open position and it's stopped. That concludes the the problem-solving portion of our exercise here. A couple of things I'd like to mention to you that maybe you noticed that are not just for illustration, not just for the video, not just for looks. The lock and tag, the using of the gloves, testing before you touch. These in here, I could do the lock and tag without ever rising from the chair. In the field, it's never that easy. You have to make an effort. That's a worthy effort, though. That's a necessary effort. Don't forget, don't omit the lock and tag. Just as I use this little instrument here, test it before you touch it. Make sure. There's been several folks have been injured by circuits they thought, they believed were locked and tagged out. Maybe powered from another source. Maybe a mistake was made. It wasn't truly locked out. If you test it before you touch it. Wear the gloves. Consider the gloves the same manner you would a parachute. A parachute is a mechanical device that's going to protect you in otherwise a lethal situation. It will bring you slowly to the ground. The gloves, they'll protect you from a different but no less lethal situation. If a mistake is made, if a slip, a blunder, an error, the glove will protect you from a lethal potential. Calibrate your instrument. Read the instrument. Note the difference in the readings. Follow the print. The instrument, the print, being safe, being alive to finish the problem, because they're all necessary. Can't omit any of the steps. Thank you.